Part will be a bit of repetition because I'm going to, what we showed in the last class was let me just check that whether we got that or not. Yeah, we had that in the last class. Now our equation was minus u0b upon 2a times f plus u0b upon 2a zeta f prime is equal to g prime. This was our equation, if you recall. Just check up. एक मिनट सब लोग अपनी किताबों में देख लो if we had this or not. तुम नहीं थे तो तुम्हें तो बहुत मतलब. See, this basically what we have done is we have non-dimensionalized the u0 minus mean u divided by us. We wrote that as f. And the Reynolds stress u prime v prime suitably non-dimensionalized was written as g. So divided by us square. G is a function of, so we talked of self-preservation. एक मिनट मैं 2 मिनट बता ही देता हूँ. Let me go to the okay. So a bit of repetition. We're talking of self similar quantities. So what we assumed was in the wake, and we are talking of far downstream, where all the velocity profiles, if you look at it in terms of functions of y and x, will collapse into a single curve. So that is what we were trying to determine, this how to get the profile for the mean velocity. So we wrote u0 minus u upon us as some function of y by L. Now notice y by L is also suitably non-dimensionalized. L is some quantity which is a function of x. Okay. So this was the self-preservation thing, and then in our equation we also had a u prime v prime. So we would expect u prime v prime also to be self-similar. So u prime v prime divided by us square was written as some another function of y by L. So this basically wherever there is a g, think of it as the velocity or as the Reynolds stress, and f as the velocity defect. That is what f and g imply. And from here then, when we use the self-similarity hypothesis, and this you'll have to look at the lectures, we substituted them in the momentum equation for the wake. So basically we are solving this equation, what I wrote today. The first thing is the appropriate form or suitably non-dimensionalized form of this equation. Because there is a f g prime, so this is a d by dy of u prime v prime, and then there is a du by dx, so that gives us f prime. But then because of the non-dimensionalization, that is how we will get it. Okay. So this is what we had done. So that is the equation, and then we derived the condition under which we will have self-similarity. That means all the coefficients of this equation, we wrote everything in terms of f of a non-dimensional variable zeta. So everything which comes, and all y's were eliminated. So there were only two variables in the equation, zeta and x. And wherever x came, functions of x came, we said that should be a constant. Only then we will get this self-similar solution. So we got two conditions. There were two variables, us and L, which depended on x. So we assumed a power law profile. So we assumed L goes like x to the power of n. And when we substituted them in these equations, what we got was us then has to go like x to the power of n minus 1. Okay. And then what happened was we needed a second equation to find n. First equation came by balancing the terms in the equations. And I don't know, you must have done the boundary layer, this thing there also we have the self-similar profile. And there One condition comes from balancing the viscous term and the convective term. And the second one comes from the boundary condition, that velocity is 0 or velocity is equal to capital U at y is equal to infinity. But here we don't have any boundary condition like that. But what we have is the momentum integral condition, that the total momentum flux is constant. So the momentum flux, which is u0 minus u times u dy, we express it in terms of f and zeta. And when we express this in terms of f and zeta, what we get is u0 us L times integral f zeta d zeta. The second term is of a relatively small order of magnitude because it is us square. So this u0 us L, this must be constant. And this gives rise to that the product of us times L must be constant. So us went like x to the power of n, x to the power of n minus 1, L went like x to the power of n. So when we take the product of these two, we get 2n minus 1 must be equal to 0. And from there we get the condition n is equal to half.
Why does it have to be constant?
Because again this is a self-similar profile. So these are functions of x and we don't want any functions of x. तो ये चीज़ तुम्हें इस वाले कोर्स में जेट वगैरह कराई हैं क्या?
हाँ, जेट का भी वही है।
तो जेट में भी एग्जैक्टली ऐसा ही आएगा. सो इनफैक्ट दैट्स व्हाई आई वांटेड टू डू इट. हैं? हाँ, नोटेशन थोड़ी अलग जाती है, पर यही चीज़ आएगी. जेट में भी समथिंग विल कम एंड दैट समथिंग एक्स टू द पावर ऑफ वॉट एवर कम्स दैट हैज़ टू बी 0. सो दैट इज हाउ यू गेट दैट वैल्यू ऑफ एन. ठीक है ना? जेट में भी आया हुआ, इसीलिए इनफैक्ट दैट्स व्हाई आई वेंट थ्रू द डिटेल सो दैट यू can correlate things in different courses. I'm not sure if I will do jets here, but if we do jets, then something similar will come in jets also. Okay, so this is where we were, and when we put everything in the equation, we got this equation, and this is what I wrote today in the class. कहाँ पे? दोनों तरफ माइनस है या एक तरफ माइनस है? माइनस जी प्राइम लिखा है और दूसरी तरफ क्या है? दूसरी तरफ भी माइनस है क्या? नहीं है. देख लेते हैं एक मिनट. लेट्स जस्ट सी. सो दिस इज द इक्वेशन. नाउ हियर u0 ऑफ कोर्स वी हैड assumed to be constant. b and a are constants because they are the coefficients of us and L. Okay, and then we get this equation. And this is where yesterday I said, and again when I did this, and then we used one more argument to convert g as a function of f. We use the concept of eddy viscosity. Okay, so I'll come to that, but so this g is basically d by dy of u prime v prime. Okay, now if I use eddy viscosity, then what I get is minus u prime v prime is equal to nu t du by dy. That's the definition of eddy viscosity. So therefore, and here using empirical relation, basically what we sort of assume is that if I write u prime v prime, let me just see, u prime v prime was written as g suitably non-dimensionalized and du by dy was f prime. So when I put all these, I get nu t is equal to minus us L g upon f prime. And us times L we know is a constant. Okay, and so we put eddy viscosity is a constant, and this in fact I told you how this comes from is using this definition. So है एफ कौन सा दूसरा कौन सा यूज हुआ है? यही एफ है. अच्छा, ये ऐसा एफ और ये एफ बोथ आर सेम.
Actually, why we are equating Reynolds stress with the eddy viscosity?
Oh, because this is some sort of modeling. That is how we define eddy viscosity. Eddy viscosity. So again, that means we are using some sort of an empirical relation, that we are forcing this equation. See, that is what eddy viscosity is all about. When we model turbulence, we write u prime v prime is equal to nu t times du by dy. Now, if that's a good model or a bad model, we don't know. But that is what we use. And if you look at it in chapter 3, that is what we have done. That's how we wrote eddy viscosity. And then what it turns out is eddy viscosity is just a function of zeta. That means it's a function of zeta is non-dimensionalized by. Okay? So eddy viscosity is a function of zeta. And then we made an assumption that eddy viscosity, we assume that to be a constant. So now I wrote the solution of this, and I was not able to give you how it came. And that's what I'm going to do today. So this was till the last lecture. Now I'm continuing in today's lecture. Let me see. So, no, this minus comes because this minus was there yesterday also. Then what you do is you write it in this form, u0b upon 2a common into f this. Oh, okay, sorry, you are right. This equation, both the terms are plus. The equation before this, where I put this, but I've already done that in the last class, so I'm not. This term is not minus. Minus came in the equation before this. Yeah, we have already done this, so you're right. And this G prime, we will convert it in terms of F double prime, but that will come later. But let's see now. So now let alpha 1 be equal to u0 b upon 2a, which is a constant. So we have alpha 1 into f plus zeta f prime is equal to G prime. Now, how do we integrate this? And this is where I was, can anyone think of a mathematical trick by which this becomes integrable? Can I write this bracketed term in a simpler form? Can it be written as a total derivative of something? Zeta तो zeta से फर्क नहीं पड़ता ना. G and F are functions of zeta. It's just a variable. Zeta is basically y by L, but it doesn't matter because here the equation is an ODE in zeta. Can I play with this bracketed term? Can I write it as a total derivative of something? Because on this side we have G prime. Just सोचो इसको. What is the derivative of zeta f का derivative क्या होता है? Zeta times f. What is d by d zeta of that? So now what I'm saying is you have to find the d by d zeta of, what is that? First is zeta का derivative is 1 times f plus, what do we have here? So that means this quantity can be written as zeta f prime. And today Rakshit is missing. He was asking me, will you ask this in the exam, how to derive it? Now I can ask you. Okay, so this gives us alpha 1 times zeta f whole prime is equal to G prime, and now I can integrate this. So I will get alpha 1 zeta times f is equal to g plus a constant. Okay, that's fine. Now, what we know is as zeta tends to infinity, f goes to 0 and g go to 0. F is the mean velocity defect that goes to 0. G is the Reynolds stress. We know outside the turbulent wake the Reynolds stresses are 0. So that means for large zeta, this is 0 and this is 0. That means the constant will be 0. पूछ रहे हो?
This means that far downstream there your L will be very small.
हाँ.
At that point your zeta is going to infinity. Because zeta is y by L.
Zeta is y by L, small l.
Yes, small L.
So this is basically something like this. Small l is some representative length here. So
So when you are assuming it far downstream, then you are
far downstream, this L is going small.
going small.
Huh.
So at that point your zeta is going to be
But then this length y will also become small. Only y is becoming big. Yeah. So far downstream, yeah. So we have zeta will go to infinity. Okay. No, y by L. Huh? L is something finite here. Small l, zeta y is this distance, L is this distance, small l is this distance. नहीं, y by L तो हर बार. See, what I'm saying is zeta represents this thing. So outside zeta infinity really represents outside the boundary layer. मतलब, so again these infinities here are asymptotic terms because L is also small, as you rightly say, small l is small. So infinity in variables which are close to this thing. There are two variables, inner variables and outer variables. So the infinity sort of makes two different meanings in terms of the two variables, and then this implies that the constant is 0. So we have alpha 1 zeta f is equal to g, and now we put that g is equal to minus fi by the turbulence Reynolds number. This comes from the definition of eddy viscosity, because the eddy viscosity goes in RET. RET is U times L divided by nu T. Okay?
सर ये नहीं समझा zeta tends to f tends to 0 और g tends to 0 कैसे है?
F क्या है? वेलोसिटी डिफेक्ट. सो जब हम वेग के बाहर आ जाते हैं तो डिफेक्ट जीरो हो जाएगा और रेनॉल्ड स्ट्रेस भी जीरो हो जाएंगे. ठीक है ना? सो दैट्स हाउ वी गेट दिस. सो now what I can do is I can write alpha 1 zeta f is equal to minus f prime upon RET, and I can write f prime is equal to alpha 1 times RET times minus zeta f. And this alpha 1 times RET is what I wrote as alpha in the last class. So that is why I used alpha 1 today, because it was without the RET. So f prime is equal to this f prime is equal to minus alpha zeta times f, and this I can write it as df by df, take the f on both sides, is equal to see, we always do this whenever You have f and f prime. You take all the f's on one side, take the independent variable zeta on the other side. And this gives me log of f is equal to minus alpha zeta square by 2 plus constant, and f will be equal to c1 exponential, and this is what was the form. We're not able to, I just wrote it last time, but now I have derived it. Now to get C1, what we know is we defined f as the defect u minus u0 divided by us. So at 0, u minus u0 is nothing but us. So f of 0 is equal to 1. What does that lead to? If put f of 0 is equal to 1, C1 will be 1. So this implies f is equal to exponential of okay. So this is the expression for f which we had gotten. Now, based on this, now if we continue here, now we, if and we choose L such that alpha is equal to 1. So to get rid of alpha, alpha was u0 a upon b, there were some constants. So we choose L. L is a length along the y direction. So we choose it in such a way that alpha is equal to 1, and that leads to f of 1 is equal to exponential of minus half, which is nearly equal to 0.6. And the experimental data gives the value of RET is equal to 12.5. We have assumed nu t is equal to constant. So therefore, u times L was also constant. So UL upon nu, when you do it, you get RET, and that is a constant. And this we try to get from the experimental data, and that gives us a value is equal to 12.5 for these bake flows. Now, what we try to see is how much is this correct or not. So what we do is, if we plot f as a function of zeta, so this is the graph for exponential minus zeta square by 2. At zeta is equal to 0, this has to be 1, and then it has to drop exponentially. This is the graph. So this is the theoretical graph. Now experimentally what we find is this red line, this shows experimental data. So what we observe is for zeta less than 1.3, the experimental data almost matches with the theoretical curve. But beyond that, we find that f, the defect, is less than what is predicted by the data. And here, if we try to find the reason for this, so come back to the black pen. So the real profile or experimental profile of the velocity defect matches well till and the reason for this deviation basically is that we have assumed nu t is constant now. If we look at the no, so for the graph is what I mean by theoretically is that f is what velocity profile. So that profile matches exponential minus half zeta square up till zeta is equal to 1.3. That means now for different values of x, once you are sufficiently downstream at this location, this location, this location, if you plot the mean velocity defect and zeta is this dimension, so up till zeta of 1.3, which will be somewhere inside the flow still, inside the boundary, it will be inside the wake flow, it matches. But beyond that, the mean velocity profile does not match. And that is a small deviation, the shape is still the same. And the reason that's what now I'm trying to give, that we have assumed nu t is constant. Now nu t is what? Nu t tells you u prime v prime, the ratio of u prime v prime and mean velocity gradient, or the other way around. Okay, nu t is equal to the ratio of u prime v prime to du by dy. Now, the logic I'm trying to give you is that this is, I should not show central line, this is the line y is equal to 0 or zeta is equal to 0. Now, if I go to this length, then somewhere here I get a region where the turbulence is diminishing, and beyond this there is no turbulence. And if I look at the actual shape of this wake, this is how the wake looks like. So now if I am at a particular y, far away, if I fix a value of y, now what I'm finding is in this region, we are in the turbulent zone. Then we come in the laminar zone. Then we come in the turbulent zone. Then we come in the laminar zone. Then we come in the turbulent zone. So that means such a phenomena is called intermittency. That we are not at all the time in the turbulent region. Outside the turbulent region, Reynolds stresses are 0. We have assumed nu t is equal to constant. But far from here, what will happen is nu t, in this region it will be the same nu t, but here it will become 0. And then it will be the same nu t, then it will become 0. Okay? So that is what sort of a phenomena happens. So near the edges of the wake, we experience what is termed as intermittency. That means for some time, and intermittency is the equal to time the particle is in turbulent zone divided by the total time. So if I am close here, what will be intermittency? If I am at this location, as I go down, I am always in the turbulent zone. So the time I am in the turbulent zone and the total time, both are the same. So intermittency will be 1. But if I come here, somewhere here, then I will have to see if I'm at a location which is at this location, something like this, then intermittency will be like 0.8 or 0.9. But once I come here, it will be, let's say, 0.7. And then once I'm outside here, what will be intermittency? It will be 0. Okay? So we have this, and therefore the correct expression, or a better expression, I should not use the word correct, for nu t is equal to gamma times constant. ये गामा लिखा है, small gamma. Now this sort of, again, I could have skipped this, but intermittency is something you encounter in many other phenomena also. In many places you encounter intermittency. It is something like, often there is a release of pressure. And when that release takes place, you say, and then it's not like a pressure cooker when it goes. The whistle of the pressure cooker, for the time it blows, divided by the total time, can again be defined as some sort of an intermittency. When pressure becomes high enough in the pressure cooker, it is released, you hear the whistle, and because the pressure is released, the whistle goes down, you stop listening to it. After some time, because the heat is continuously on, you again get the whistle, and if you take the ratio of the time of the whistle to the total time, that will give you intermittency in that context. So intermittency is used in many contexts, in many, this thing we are using it with respect to time, you can use it with respect to space, but often it will be encountered. Particularly when you have things, and often what happens is things move from a stable to unstable zone through intermittency. Okay? So this sort of, and here also, because we are at the edge of the boundary layer or edge of the wake, there is a turbulent wake outside which flow is laminar. So because we are at the boundary of these two zones, that is where the intermittency comes in. If you are totally in the laminar zone or totally in the turbulent zone, there is no question of intermittency. Yeah. So in this one,
So what is the ends of these two graphs saying that in the experimental data your F is
so what I'm saying is up till 1.3 experimental data, up till this, in fact this top line was just an error. I draw exponential minus zeta square by 2. Then what I find is the experimental data up to 1.3 matches the graph, matches the theoretical curve. But beyond that, there is a discrepancy. And this we explain because once we are beyond zeta is equal to 1.3, we start falling in the intermittent zone.
So my question was that this black graph you are showing that it is not touching the horizontal line and it's
No, so this also will basically be asymptotic.
it will be similar.
Both of them will be asymptotic. So even this red one, probably I've made a mistake. This should also be some sort of. That's what you were asking? So the red one is not intersecting like this. वो भी ऐसे ही होगा हल्का हल्का सा मतलब asymptotic होगा. Okay. So now this is what is intermittency. Now let's see, is there anything more we can learn from this? So there are certain more things we'll get in terms of mean quantities. What is, let's look at gamma could intermittency factor. Na? Gamma is called intermittency. And इसकी definition आपको बता दी ना. Time when the particle is in the, if I follow one particle, the time when it is in the at a particular y, or actually I should not be even calling it a particle because the particle will probably move randomly. If I look at a y, if I look at the speed at which you, how much it will stay in the turbulent zone, or at a particular y, how much is the turbulent zone divided by the total space. That is what will give you the intermittency. So this time was probably to make it more physical. Now, also what we, let's see some more things we get. If we look at minus infinity to infinity, f of zeta d zeta, this is equal to this is a definite integral, and this can be, we cannot find it in a closed form, but this is related to the error function, and these are tabulated values, and this number turns out to be equal to root 2 pi. Okay, and we had this us times L integral minus infinity to infinity f of zeta d zeta was equal to minus u0 by theta, and when we put this in and we put this expression, let's see, where am I here? From here what one can get is, if I look at L by theta, it turns out to be equal to 0.25 x by theta to the power of half, and us upon u naught turns out to be equal to 1.06 theta upon x to the power of half, and theta is the basically momentum thickness. So we can get these expressions. ये रुक क्या वो चला गया रूट ऑफ 2 पाई है आ गया क्या नहीं आया I think this is hinting to something. This is hinting that let's go and have a cup of coffee. I'm not feeling too well. तो क्या पर चलो. I think I'll stop here today. इससे अगली बार will see there are many things in the book. What we now do is we have an form for Reynolds stress and for the mean velocity. So next what we do what we do is we look at the turbulent kinetic energy budget and try to see how the different terms are varying with zeta. There's a production term, there's an advection term. So we'll go to the turbulent, but again, at many places to make those estimates, we will use this form of the profile, but we'll also have to use some empirical data. So, like for example, to get to the estimates of kinetic energy, we'll need what is u prime v prime divided by the correlation coefficient of u prime v prime. So, u prime v prime divided by square root of u prime square, square root of v prime square. Some of these data we will have to use empirical relations or experimental data. Using that, in the next class, we'll do the equation for the total profile, the kinetic energy budget, and look at how these terms come. And again, the relevance of these for some of you people is that when you talk of turbulence and you derive different terms, of course, you will calculate all this using CFD. So, you will not be, see here, in some sense, the beauty, or I don't know whether you call it beauty, is that by feeding in the equations, we are able to get an analytical profile. But to get to that analytical profile, we had to really do a lot of assumptions. We made self-similar assumptions and all. Only then we can get an analytical profile. Now, probably 50 years back or 60 years back, when we did not have enough computational resources, doing these analytical profiles was very elegant. That you are able to think up of a solution, you think of a differential equation, and the differential equation is already there. Like we saw today, it was a very small thing. It was a simple zeta f whole prime, which was nothing very big. But you think of these solutions like this. So that was the elegance in the old days. But today, is this elegance needed? Is a question thing, because we try to solve the equations directly. We don't bother about trying to write to all these self-similar forms, etc. We'll just brute force feed in the equations and the modeled equations to get our profiles. So that is, so we will have a look at some more of this, just some more of this elegant and beauty things, and then for the last couple of weeks we'll look at the modeling of Reynolds stresses, where we will assume that we are going to just use brute force ways to solve the equations on the computer, and then what is the equation for kinetic energy? We have already derived that equation for dissipation, etc. And from there we will get to the models. Of course, we have already introduced Newt, we have introduced the eddy viscosity model. But then how do we express eddy viscosity? Here for the jets, it turned out, or we assume it is constant. Constant in the sense function of zeta. Okay, but then will this always work? Otherwise, how do we assume eddy viscosity? How do we find that? And that is what we will tell you. Okay.